So yeah, hey everybody, welcome to the workshop. As he introduced me, I'm Jetzork. I'm working for the Deutsche Telekom as a DevOps engineer. And yeah, we had the challenge that Deutsche Telekom has a huge backbone with a lot of virtual routing forwarding instances within the backbone on the different routers. And we need to hop on the SONiC architecture there. And at first, I'm working there in the Telekom in a team which is called Das Ship. For all who is not native German speaker, Das Ship is calling meaning the ship in English. And the project is also known, or the team, as TCAS, Cluster as a Service. And we are an internal GitOps-based Kubernetes cluster as a service platform, which is there to onboard network technology workloads like the 5G core, 5G campus, and as well PCF, for example. And we try to do it by using almost exclusively open source components. And currently we have more than 150 clusters up and running, which are providing more than 40 apps. And we have around more than 170 SONiC devices which are OCP accepted. If we go over to the next slide, you, I guess, see network architecture which you know in a quite high abstraction. On the left side, you have different networks, which could be, for example, different backbones, a company backbone with multiple VRF, like in our case. In the middle, we have just here firewall, which is representing for the picture a 3-tier architecture. We have currently still locations in a telecom where we have an aggregation layer where the access switches are applied to. In the distribution layer, we have the distribution switches, firewalls, and load balancers. And on the top, we have the core layer, which is connected to our different backbones. On the right side, you can see a pipe, which is representing a VLAN, but it could also be 5 VLANs, 3 VLANs, whatever. And they will then be connected to the different servers, for example, worker nodes, and they are currently configured as trunk ports. Our worker nodes itself are running Calico in full mesh based on BGP, and the connection is also depending on the location. Sometimes it's IP and IP, or VXLAN used to have the cross communication between the different nodes. We thought about that isn't a good solution, and it's quite some static configuration of firewall, like the interfaces needs to be created, and a lot of other stuff. The trunk ports need maybe, or the switches, the VLANs needs to be added. And for that reason, we thought about something which is more dynamic. You can see in this picture that the firewall is thrown out here, and in the middle there are 2 switches right now, which are representing a cross fabric. It's just something like spine leaf architecture. On the left side, you can see still the same networks, which in our case are company backbones, different backbones with multiple VRFs. And on the right side, we exchanged the VLANs with VXLANs. And when we go from the bottom up, we have one specific VXLAN per cluster or tenant, which is only responsible for the routing of the cross-cluster traffic. And then we have per connected VRF an additional VNI, which is pointing to the specific VRF. And the VXLAN itself is running in combination with EVPN. And for this presentation, we are only focusing on EVPN type 5, which is the nearest point to cloud native. And we still have other solutions like SRIOV or MacVLAN, but that's not here. We could maybe have a talk about later on that. You can see still the workers are connected below. They are just connected now to different VXLANs instead of VLANs. And if a pod has an IP, which needs to be announced to the different backbones, he will directly announce this IP into the cluster VXLAN. Then we go a bit deeper in our layout. You can still see then the appearing VRFs in our network backbones. We have, for example, a network 1, A, B, and C, and network 2, X, and Epsilon. And then you see the border leaf. The border leaf will have BGP numbered peerings to the different backbones, including different peerings to the different VRFs. Also, the border leaf is wrapping them up into different VRFs. And as I've mentioned earlier, every VRF will have a unique VNI ID for the BGP EVPN type 5 session. And then the spine leaf fabric is in the middle. At the end, we have the leaf where the worker nodes are connected to. In this picture, you can see just 4 connections, but in reality, every worker node is connected by 4 times 25 gigabyte to at least 2 switches. If we drill down again a bit deeper, you can see our whole layout of our spine leaf fabric. On the top, there is a border leaf, as already mentioned, which has the different connectivities to the different backbones. Then in the middle there's a spine switch, which is collecting all of our leaf switches without the exception of the leaf T-base. To save some spot on the spine switch, we just connected them to the leaf because they are something like management switches in our case. When you have a look down on the server which are connected, in this case also worker, you can see purple lines which are named here with access VLAN because it's the lighthouse management port of the server. And we provide from the leaf T-base a static anycast gateway to forward the traffic from there to the different backbone. And for that reason you can see also the purple arrow on the left side, because after the packet hits the leaf T-base, the switch needs to know how to forward this traffic, and for that reason we are stretching down the management VRF to the leaf T-base. In the middle you can see the green arrow which is pointing from the border leaf to the server, because the server is participating in our fabric as well. Our fabric is completely working with BGP unnumbered, and it's split it into underlay and overlay. The underlay is just knowing about the different loopback IPs of the server, of the switches, border leaf, spine, whatever. And the overlay then catch in and knows everything about the routing to the outside world. And when we have the VTAP on the border leaf, we will also configure the VTAP on the server, configure there the VNI the application is in need for to have connections to, and also configuring there the VRF. Beneath the north-south traffic, we have also east-west traffic. In this picture you can see it, for example, for the leaf T-base, because our lights-out management interfaces are connected to a bunch of leaf T-bases and all are sharing the same subnet to have an IP from. We need to make the fabric aware of where the lights-out management interface is connected for real. And if we have, for example, LOM interface connected on leaf T-base 1, due to the equal cost multipassing we run in our fabric, it could be that the packet will arrive on leaf T-base 4. Leaf T-base 4 wouldn't have any information about that without the EVPN type 2 session in between. But for that reason, EVPN type 2 will advertise the MAC addresses and also the upper entries, and leaf T-base 4 will then forward the packet additionally to leaf T-base 1 to reach out to the connected lights-out management interface. And from the slide before, you can see that we have the BGP EVPN type 5 connection as well between the different worker nodes to exchange the traffic which is coming from, for example, pods to each other worker node. Here, if we drill down again a bit deeper, we have some configuration examples which are really on a high level. There is a lot of more configuration in place than shown up here. On a border leaf, for example, you have the internet interface VLAN 50, which is just a dummy, which is required for SONiC. And you can see that we add the command now autostate because we want the VLAN to behave like a loopback interface, that it's not going down if there is no interface available, because the border leaf itself will never have some connected access ports or trunk ports. And yeah, when we jump over to the next box, we have the interface weakstand configuration, which is just named here VTAP1. And we have at first the VNI VLAN map, where we are pointing out that VLAN 50 is pointing to VNI 50. And we have the VNI VRF map, where VNI 50 is then pointing for VRFA, which is in this example maybe a BGP, a management VRF. And this configuration indicates already for the switch that this is a EVPN type 5 session, because we defined a VRF in here. And in the right bubble you can see just the needed configuration for BGP for the specific VRF. We enable the address family L2 VPN EVPN, and we will set up the command, for example, advertise IPv4 unicast, which take care of that all the routes which are in the specific VRF will advertise through the BGP EVPN to, in this case, the destination, the server. Beneath the advertise IPv4 unicast, you can also advertise the IPv6 routes or prefixes, which we are also doing in our fabric. And as I've mentioned, the server is participating as well in our fabric. I guess I mentioned that they are also connected by BGP unnumbered to our fabric. We are running on the different servers as well the free range routing, shortly FRR. And to have everything in place, we have at first a lot of netlink configuration, which will create a bridge for the VRF, which will create the VXLAN itself, which will create the VRF itself. And you can see in the bottom of the corner from the the left one where the bridge cluster is described. You can see an IP that would be, out of our point of view, the IP where the node itself is reachable for. We have something in the network 1, also a control plane of Kubernetes running, and this needs to establish a connection to the different nodes, and that would be the IP which is used for that. And for the reason this IP is also sometimes not even used only within the VRF-A. For example, it's also something we want to connect to storage. Then we would have an additional VRF which is called, for example, storage. We place this IP in the default table and create with a virtual Ethernet pair of a VRF-A definition at default VRF-A the connection between the different routing tables. And when we move over to the next box, that is a small piece of our free-range routing configuration. We have, for example, the VRF-A again, which is necessary for this example. And we telling FRR that VNI 50 will be a part of this VRF. That's everything so far. If we go now to the next box, the right side, for the router BGP, you can see that we also enable there the advertise L2 VPN address family L2 VPN EVPN. But instead of the border leaf configuration, we are also adding a route map for the command advertise IPv4 unicast, because we are doing some filtering here, that not all IP addresses of the worker node will, for example, be advertised into the specific VNI, because the cluster can run more than a single VRF. And if we mix up the IP address, we maybe get conflicts which are already sometimes there, because in the different VRFs we have sometimes duplicate IP addresses. For that reason, VRFs are there, but it's sometimes making lives harder. If we are now going over to the last slide, you can see the border leaf configuration, which is still the same like in the previous slide. On a leaf T-base, there is just a different configuration. You see, in addition to the VLAN 50, that we have VLAN 10, for example, which is also configured to be a part of the VRF-A. We also do in here the command now auto state, which is aware of that the interface won't fall down. It's not quite necessary, but it's ensure some stability. And in addition, we configure then the DHCP relay, because the light source management interface don't even need to care about static IP addresses. We just let them come up, send the DHCP request. Our DHCP server is also located within the VRF-A in network 1. Then the packet is reaching out there, and the IP address will be assigned back to it. And at the end, we have the Anycast address, which is the static Anycast gateway. This is configured also on all leaf T-bases, the same IP. And in addition, we have the interface VLAN 50, which is, as I mentioned, the EVPN type 2 type 5 connection. It's also here configured with an auto state and to the VRF. But at the end, there is a difference in the VXLAN configuration. Previously, we had only VNI VLAN map, which was pointing to VNI 50, pointing to VLAN 50. In this case, we have also the VNI 10 with VLAN 10. And for the reason we don't have a VNI VRF map for that specific VNI, it indicates it's just a EVPN type 2 connection in here. As I've mentioned earlier, there is a lot of configuration which is there as well. On this slide, there's also no point for the BGP connection, but it's very similar to the slide before. And also the BGP VRF in default needs some configuration. We're advertising there all VNIs as a command. We have the complete configuration for the BGP establishing which interfaces will be used and so on, but that's too much for this presentation in here. And now we are through. Thanking for your attention. Hope you liked it, and if you have any question, don't hesitate to ask them. Thank you. I guess.
From my understanding that you're using VXLAN on the servers, yes, VTAP on the servers.
Yeah.
What is performance on each servers? How many gigabits on VXLAN can you go on each server? And the second question is, do you use VXLAN offload on network interface card to enhance performance on each server?
So currently it's everything in software, as far as I know. We have a different mate of our team, which is much deeper in the stuff around the server, which is mainly developing the stuff and bringing everything there, because we had a lot of problems with the free-range routing from the open source stack. We had some bug fixes there, which was then later be killed again by new release. And with regards to the performance, we run a lot of performance tests because the 5G core will be enabled there, and we don't face any issues yet. But I don't have right here some specific numbers, like whatever 20 gigabytes will fit or something like that. If you are interested in that, don't hesitate to write me an email, and I will get in touch with the mates who are doing that and provide you then the information.
Thank you.
You're welcome.
What kind of SONiC version are you using?
We are currently using, that's maybe something I forgot to announce, we are using in general the switches from the vendor EdgeCore, and we started also with the EdgeCore SONiC, but we had a lot of problems with that. We then went over to Broadcom because they are the only vendor which we currently know which are offering the feature set we really need. And we are currently in the version 4.0.2, but we are waiting still for a newer version because there is a bug fix in it. We are facing some problems with IPv6 and our Mellanox cards within the server, and with that version this will also be changed. Currently we are running a fix on the worker nodes, but then the fix is also in SONiC available because they will announce sometimes often the neighbors facilitation.
So I have a simple question. Do you go EVPN down to the servers, or you end on the top of the rack?
No, the session for BGP EVPN ends on a server. So we have the first session on a border leaf where everything get encapsulated, and then at the end we have the server itself, which is also then configured to do the BGP routing for EVPN.
Thank you.
You're welcome.
So he basically stole the first part of my question. I wanted to ask the same thing, but then following up to the answer, then why do you need any EVPN type 5 whatsoever on the leaves if you are extending all the way to the server for EVPN?
Yeah.
Why don't just extend the underlay to the server?
So in that case, between the leaf we don't have EVPN type 5. It's on the slide, it's EVPN type 2. EVPN type 5 is exchanged in layer 3 routes out of the VRF. But for the connected leaf T base, the server won't participate because it's just lights out management interfaces. And to exchange the information with EVPN type 2, the MAC addresses and the ARP entries, we need that connection in addition. And we will have also, you can see the leaf part in the middle is empty. We will have something like the same stuff on the leaf in case we are running SRIOV, because then the server is not able, or the pod, to announce its IPs, to announce MAC addresses and so on, because the packet will arrive through the trunk port on the leaf, and the leaf is then the first entry point. So the server is not able to handle such a traffic. It's not possible. So for some special use cases, it's mainly EVPN type 2, or it's only EVPN type 2. We have additional configuration on the leaf switches, and that only to exchange the MAC addresses.
All right, thanks. That was clear for the leaf T. I was talking about the leaves because on the subsequent slide, it looked like on the leaf you actually had the type 5 configuration, which I might have seen as a mistake.
Okay, maybe.
Sorry.
Yeah, no problem.
Thanks.
Maybe next one.
So judging from the number of SONiC devices and the number of servers and the number of involved services to establish all of that BGP, there must be quite a lot of configuration. How do you manage that complexity, and how do you apply the configuration there?
So that's a good question. We have later on Chris talking, who is also working for our company. He's coming from Weaveworks, and we created a lot of automation for that. We have at first Jetzork running locally in our company, where we're templating out the ZTP configuration. Currently it's much more because the follow-up for the day 2 operation, the SONiC operator is not in place yet, which is built out of the operator framework. And So the first step is the switch will be plugged in, the ONI network installer is running, then from the DHCP relay the switch is receiving the information where he needs to pull his SONiC version. After SONiC is installed, ZTP kicks in, and then we provide a JSON file where it's written, please install this SONiC version again if it's maybe different. We tell them please do some management stuff to provide keys and so on, and at least the configuration. And this configuration is built out of Jetzork, which is a Git repo. We do it then by CLI, change some stuff. Then we have a pipeline which is generating the configuration and checks if the configuration is valid. And after that's finished and the merge request is merged, it will then be pushed to our Artifactory. And we have a container in the middle where we just grab the data from the Artifactory and provide this data then to the switch. And for the day 2 operation later on, when we change, for example, an interface from cloud native to the special use case SIOV, we need to reconfigure this interface. That's currently also done by ZTP, but that causes a short downtime because the switch will be reinstalled and the config needs to be reloaded, which is just breaking everything. And that will be then also carried over by the network operator, which will be shown later on, that the configuration for IPv6 enable will be disabled to run BGP unnumbered, and the switch trunk port configuration will get in place, as well as stuff like TACAX, NTP, and so on will also be then rolled out by the network operator instead of using ZTP.
Pretty cool. You use the same configuration for the server side?
No, for the server side, we have something which is part of the of my session tomorrow. We have a network operator that's open source. It's Shift network operator. You can Google it. It's developed by made out of our team, which has also more information around the throughput, I guess. And we have some custom resources out of Kubernetes. Where VRF is defined, where the layer 2 network definitions are defined, the site configuration is assigned, which VRFs are available, which VNI will be addressed or assigned to the specific VRF, and out of that there will also the configuration generated, so the netlink commands will completely drop out. The necessary configuration will also be done by another tool which is called NetPlanner. The initial setup is done by that, which is also from our company. And due to that, we have for everything which we are running right now automation, because in his presentation later on, there is shown that each switch, or at least the border leaf is the largest one, is around 8,000 lines, I guess, or maybe 9,000 lines configuration. That would be too many to do it manually. And of course, by 170 devices, we would do a lot of copy-paste issues.
Okay, thank you.
Yeah, of course.
So for your VRFs, are those two separate internal tenants or actual customers, sort of?
It depends. It's sometimes customers, sometimes it's internal traffic. We have a lot of these. For example, when a mobile customer is coming to us, he uses another VRF than a normal customer out of the fixed line world. And we have also something for our internal communication, machine-to-machine communication, for example, which is also then a separate VRF because our security likes to have it secure. And yeah, due to historical reasons, we have a bunch of them. But it's to separate nearly everything. It's not only customers, it's only internal stuff. It depends.
And for the type 5 routes, when achieving the separation for in the BGP properties, are you achieving that separation in the actual mapping of RTs, or are these route targets or route distinguishers through reusing the same VLANs across your networks, or like VRFA always gets VLAN 50, VRFB always gets VRF 60 kind of thing?
So the route distinguisher itself is just defined automatically from SONiC. We don't do it manually. SONiC does it for us. We try to keep on all locations the VNI ID is the same, because it's easier when management ID is, for example, 50, that it's on all the locations the same, because if you have a troubleshooting in the night at 3 a.m. and it's sometimes 50, sometimes 60, sometimes 70, you won't have an overview about that. And I guess I've missed the rest of the question. Maybe you can repeat what the rest of the question was.
Are you reusing the properties? So that was it, I guess. I mean,
What do you mean with properties?
like, so you answered the first part, right? You're reusing the VLAN IDs and VNIs.
Yeah.
So that you know that VLAN 70 is always VNI 70
Yeah.
across the board. And then route target properties, and I guess SONiC is doing that automatically,
Mhm.
you said, right? So that's
Okay.
it.
Thank you.
Please, what is the size of the team who is responsible for this solution?
So the solution is completely done by our internal team, does Schiff. We are around, I guess, 14, 15 people, I'm not sure. We got some new people in the last time. And we are also currently are responsible for the whole stack. We did compute, we did networking, we did the architecture, we did the automation and so on. But for the reason it's too much with the amount of devices we have as well for servers, as well for the network and so on, we are handing some stuff over to other teams. And yeah, so we, the Schiff, are responsible for everything right now. And it will also be the same.
One more question for me. You showed how you were able to eliminate the firewall, but by doing so, where do you place now inspection and where do you enforce any type of security and policies?
So we have a lot of stuff at first on the Kubernetes cluster when we just stay on a location. We have the network policies there around, which is carrying the most of the stuff in general. And for the stuff which is not the network policies, we have in our backbone already something like DDoS detection and so on, which is then done in that place. In the fabric currently itself, how we call it, there is no deep inspection or something planned right now. If it's planned, we need to tackle that challenge again. So, yeah. The last one, and then I will finish.
Thank you. So I understand you're using the Broadcom Enterprise SONiC.
Yep.
What are the features that you missed in the community one that made you obviously had to use this commercial version? And just name the most important one that we're missing if there are too many of them. Thank you.
So I didn't follow up the upstream status right now, but as we started, the DHCP relay was not working, not able to be sticked into a VRF, and for the reason we have a lot of VRFs, it was a requirement for us, and Broadcom solves this. That's the main reason we switched over. So I guess I'm already over time, and yeah.
It's also a small appreciation from our team, yeah? Really
Yeah.
appreciate.
Thank you. Versuchen ist besser.